Million. यार अभी तक ले आए. So, good morning all. Good morning all. We welcome you on till the fifth day. I hope so. You would have completed the assignment and submitted successfully. So, how many were able to complete the assignment? And how many find the difficulty actually more better? Who find the difficulty, please mention yes so that we can address the problem. If there is no problem, see, you are able to do it, that's perfect. Even if you are not able to do it, then definitely we can again work upon the thing so that you can. Yes, see, yesterday we started, that was only the question in the assignment. You see, instead of putting the many questions where the participants are overloaded with the thing, we are basically making the learning process smoother. It is encouraging. Once what we have read and once we are able to implement it and do it, it actually gives back us the confidence, right? So, and we are able to appreciate what type of calculations, what's going on. Because definitely when it is basically the online medium, so it is very difficult to have a one-to-one, means feel that whether the students are able to understand or not understand. So it is actually the self-assessment only which really helps. So that's why this part was given. But once you are able to do that part, then you are able to understand the very much basic of the image processing, that how does these techniques are working. What means, for example, we took up that problem. So for example, we are basically seeing the segment of, we are seeing one image. So somebody say, how can that image be enhanced for its better appearance? So this is very we say very broad question. But then somebody say, no, you can apply histogram equalization. So then first question arises, how can I draw the histogram? So once those would have done the assignment, so now you have to draw the assignment. So, draw the histogram. Histogram means basically what will come on the x-axis. On the x-axis, it will be the. So how many are able to complete it? Please mention here, those who are present. Those who did not find any difficulty, they can type yes. Okay. Amrinder, he has also completed it. Sai has also completed it. Parvesh has also completed it. It's very good. Many. Isha, yes, today some new names are there which I have not seen earlier. Isha is there. Shruti, okay, very good. Susie, perfectly. Sojalnya today he is not present. some names who are coming regularly that I'm able to find out. Aditya Sandeep. So see now see coming to the problem, see definitely. So majority are able to do it. So we again see go through it. Those were finding difficulty or see, now see we see the problem. What is there? See whenever see, we need to do the histogram equalization, the first thing we need to basically draw the R, our gray level. This is the gray level, and then it is basically the number of this gray level that is there. So here you can see here, basically this is the problem here. So that has been shown. So first, what you have basically gray levels, then what is the number of occurrence, how we have calculated it, you can very easily go through it. See, no zero is there. How many ones are there? Only it is one. How many twos are there? It is two. Three are basically two. So that we have written from this image only. So these two things we are able to do it. Thereafter, see what is total n. Total n is basically here the total number of these pixels. So how many total values are there? This is 4 by 4. So it is basically 16. So that we have written and we have divided by 16 and thereafter uh, we are able to, this is basically PDF, probability distribution function, then it is CDF, cumulative distribution function. We have added up here and thereafter we have multiplied by the 7 and thereafter we have make it a complete number. And finally, see what will be the image? This will be replaced. This 1 will replace, 0 will replace by the 0, 1 will replace by the 0, 2 will replace by the 1, 3 will replace by 2, etc., so on. So what will be the answer? So answer will be input image is this one and output image is this. So this is the problem. So this is the answer. So you have done it. Here we, this is the your assignment part, right? Now we go to our concept part because problem etc. We have kept it in the afternoon session only because since we have done the assignment, so that's why we took a bit earlier. Otherwise, we will proceed in the morning time is the best to cover the new concept, what we are going to. Today, actually, attendance is a bit less actually because since I think we are begin earlier, but to compensate that part, compensate the Sunday part, we need to. See, now coming to the part in the frequency domain. So as we just see introduce this part in frequency domain, so first thing is very much clear that this frequency domain, whenever see this thing is coming, so this is basically the removal of so of the high or low frequency component, right? What is the frequency? Frequency is basically the change in the pixel intensity value, how frequently it is changing. So many information lies in that frequency. For example, even if you see edge, etc. If you see some edge, for example, this figure is there, right? So what will happen when I will go across from here left to right? So what will happen? This value will change actually, right? Here the value will change, and as soon as because here it is boundary. Here when I will again go there, here when we will traverse in this direction, the value of the pixel intensity, it will again change. So What should we round off to an integer for the fraction value? 3.5. See, 3.5, see again, see, you should follow the same convention all the time. You can take it 3.5 to 4. You should keep it to there. Even see if you were to take it 3, it is not wrong, but better means you should be able to follow the same convention. Then what in the books it is given, it is 3.5, it is 4 on. So what we are saying here, so remember, so this thing, so a very important thing, this frequency concept in image is basically, so what happens that these edge etc. are basically, if we want to get the high frequency, minute details, then we design that type of filter. And if we want to, so what happens, you do, many approaches have been applied, for example, wavelet, etc. Wavelet and wavelet actually, it is bit, what happens in the wavelet? Wavelet is basically a, we say, uh, wave for a limited time. So you are able to get both the frequency information as well as at what time which frequency is present. You are also able to get that info. What we are saying here, that approximation of the image is basically covered by the low pass filter, and minute details and specific details of the image is basically covered by the high pass filter. That is always basically the thumb rule. Frequency domain filters differ from spatial domain filters in that they primarily focus on the frequency of the image. See, important thing that here, see, always it is what is really important. It is what is basically the frequency of the image. Then all the enhancement procedures are performed on the transform of that image. Remember, here see, we directly don't work upon that image segment, not image segment where the gray values are given. Here you work upon that frequency parts that will check. Actually, it involves a lot of mathematics. That's why I also avoided it. So now, how you first question that how you are able to do compute the transform, Fourier transform. So, for example, this image is given, fxy is there. Then you do the pre-processing. In pre-processing, what do you do in pre-processing? Basically, convert the size to some specific size. For example, it's 10 by 10, 20 by 20. You convert into a grayscale. Actually, even if it's a grayscale, sometimes some noisy values are given, 0, etc. You do the padding, etc. That is the thing. Again, actually, pre-processing depends upon the what is your final task, right? Then you take the Fourier transform. So in the Fourier transform, see what do you do? Here actually, since it's a Fourier transform, normally see the what is the formula? Formula, if you recall. Are you able to recall Fourier transform formula? Integral, yes, absolutely. What is the limit here? So this is basically a formula that x of omega is equal to x of t e minus j omega t dt, right? So this is basically the one dimensional. So in case of the image two dimensional, so this operation becomes a bit complex. But what is actually happening in the Fourier transform that we want to observe? So if you notice here, see what we are doing. Actually, we are doing basically we are doing the see if you notice here this xt what we are taking e minus j omega t dt. What do you mean by this? Here basically we are breaking the xt into the basis of e minus j omega. What do you mean by breaking? Breaking means basically I am representing. I am representing my signal into the form of the e minus j omega sinusoid. So what will be in the output? In output, actually, there will be those frequencies which are present. But what is actually happening? We are actually representing our signal, our actual original time domain signal into the basis of complex exponential. That is the main thing. Somebody say why we are so that's why we call it the transform. We are transforming one signal into one domain to the another domain. So into the form of the complex exponential. Why complex exponential? The complex exponential is such a magical number again due to mathematics that even if I do the integration, there is no problem. I get the same value. If I do the differentiation, I get the same value. D upon dt e j omega t or integrating e minus j omega t. See, such a beautiful function it is that even if I am able to do the integration, even if I am able to do the differentiation, all the things are very simple to do. That's why Fourier transform is such a popular thing. Because to convert any signal into the form of the base of the complex exponential. So what do we do? So here basically, so compute Fourier transform of image, then multiply the, but remember here, this is only one dimensional. In two dimensional, it will be double integral, right? So because see, we don't really bother about that mathematics, don't about that calculation, so that's why we are skipping it. But only we conceptual wise we should be clear that what is going on, because finally see we need to work in the frequency domain and after converting the image into a frequency component. Then what do you do? The multiply the result by a filter transfer function or simply a filter. So what are we doing? Here, see if you see in this diagram, here FUV and here filter function is there HU. So you multiply it. So what is happening here? Actually, this becomes the input. This becomes the input to a filter function. Filter function is simply a filter whose transfer function is this one. Notice one very important thing here that this small f and this capital F both are different. They have some special meaning. Are you aware? What about this small f and capital F? What can we say? This is small f and capital F. Is there any significance of this notation? No, see, transformed image, it is not basically the uh, input. F is a spatial domain, absolutely. See, F is basically spatial domain, and capital F is basically the frequency domain that it signifies. So whenever this capital word is there, you should always be alert that this capital word is basically used for the transform in the frequency domain. Whether you see the capital X here or you see the capital F here, capital H here. So whatever all the quantities are there, whenever this capital quantity is there, it means all these quantities are in the frequency domain. So what we have done, so filter function, it has been multiplied with capital F, and thereafter you take the inverse Fourier transform. What is this value? If somebody asks you HUV, FUV, this is basically the resultant image which is obtained after passing a original image through this filter function HUV. So this is basically here. Things should be clear whenever we are going it, because see, one thing must be always clear, that what is happening to the image whenever any operation is going on. What is this thing? This is basically the filtered image. So if you use basically the low pass filter, so only the low frequency components will be passed out and that will be visible. If you if your HUV is basically the high pass filter, then the only the higher frequency components will be present. So in this way, we have the total control over the image when we do it in basically the frequency domain. But what is important here? See, earlier that basically mask was playing a role. That role is played by a filter. In the spatial domain, that same mask, what do? You basically multiply it, and thereafter uh, in convolution, you flip it, and then you multiply it, and thereafter you shift it. Same thing, it is the same analogy. Here the things have been taken care by the filter, right? This is basically, so what do you do? So this is everything is in the basically frequency domain, right? So then what do you do? Take the inverse transform. See, remember, whatever processing that we need to do, that we have done in the frequency domain, and thereafter we convert back into the spatial domain. Why into the spatial domain? Because when we see the image, we are comfortable or we are tuned to see the image in the spatial domain only. If somebody asks me, no, you will be given the frequency domain representation of the picture, it would be a totally injustice to that person. For example, see, I am accustomed to see my image, my photograph. If somebody say, no, see, we have basically enhanced your image, or we have enhanced the image of your college, and instead of they say, no, we are basically providing the filtered, we are basically providing you the frequency domain picture. It will not make any sense because I am accustomed to see the things and I am accustomed to note any change, any enhancement in the spatial domain only. That's why it has been changed to the domain here. So, and thereafter you convert to, when you take the inverse Fourier transform, you get the enhancement. What is basically inverse Fourier transform? Are you aware? Just frequency domain to the time domain. Just simply I am writing the formula that you multiply x of omega. So this is the formula x of omega ej omega t dt. See, actually it's not very good writing here. Ej omega t d omega only. And is there any other factor is there? Formula? What we are saying that from the frequency domain, it's very easy to get. Simply multiply with the ej omega t, you will get it. One factor is there. Simply note it in the formula. That is basically 1 upon 2 pi. Yes, absolutely. That is also there. Only this is the difference. So this is the thing. So what we are summary. So this is basically the filtered image. So that is basically why the inverse Fourier transform, when it is saying that it is inverse Fourier transform G U of any question. So now we coming to the part basically. Now we coming to the part low pass filtering. What does happen in the low pass filtering? Low pass filtering, see, as we have discussed, now we take up basically different type of filters so that we can see the impact of them. Low pass filter basically removes the high frequency component, which means it keeps the low frequency component. It is used for smoothing the image. So what is the example of low pass filter? Low pass filter is again, see, if you, or another question, see, can we draw an analogy? Can we draw an analogy between that spatial filters and these filters? See, definitely we can draw an analogy because it is only the one operation that you are taking the things in the frequency domain. Otherwise, everything is same. Something is basically multiplication and frequency domain. Um, it will become convolution. So what we are saying here that when GUV equal to FUV, HUV, so it means basically G is basically the output when F is basically the input which is imposed on a system with impulse function this one. And this way you are able to get it. And what is its equation? Its equation is basically in context of the image that it is HUV equal to 1 if U square plus V square is less than R naught. So what we are saying here, actually, we are saying simple thing. See, mathematics is such a beautiful language that once you are able to follow it, it will give you all the answer. So see what it is saying that, for example, this is the boundary. This is the boundary. Basically, this is the R naught, right? Here it is saying that till the R naught, the value is basically 1. And after R naught, it is basically the 0. That is basically low pass filter. That's why it is represented by this diagram. Okay. Any question? And what is mask here? And important, see what is this H? HU is a Fourier transform filtering mask. It is the same mask which we are used basically in the spatial domain. But remember, there was basically you apply the mask on every segment of the image. Here you are applying that mask together in a one shot. So that's why it is shown here. What is on this x-axis? If we draw, it is omega. Now we want to see, as we discussed, that we always want to see the impact, that what is happening. What is happening when we do any type of operation? What is happening when we are applying the low pass filtering with the different value of R naught? So what we have taken the two values of R naught equal to 36, R naught equal to 26. When we have taken uh, R naught equal to 26. So it means those components which are really actually the part of the image, they would come. While in case of the 20, see 36 and 36, see what is the difference? Here the more frequencies are allowed. When the more frequencies are allowed, so that's why you are to see the more natural figure. But here, when very, very less frequencies are allowed, then what is happening? Then it is showing only the very, very basic version. Even see it has become difficult to identify that vegetable accurately. So what is basically this low pass filtering? So overall, we can say that the low pass filtering is the cutoff frequency of the ideal LPR determines the amount of frequency components passed by the filter. The smaller the value of R naught, remember, more the number of image components eliminated by the filter. That's why it becomes the problem here in this problem. In general, the value of R naught is to us such that most components of interest are passed through, while most components not of interest are eliminated. So this way. Is it making sense? Are you able to understand how do we design basically the low pass filter when we consider the image enhancement in the frequency domain? So another filter is basically the Butterworth filter. In Butterworth filter, see what is basically HUV. HUV again, see this is the another very popular filter. What it has been said here. R0 is small or information losing. See R0, yes, when R0 is small, see we will get very low frequency component, limited information. So definitely we are losing the information. So what that has been shown here, that Butterworth low pass filtering, a two-dimensional Butterworth low pass filter as a transfer function of this one. So then what do? Here see it is not Butterworth, basically you are also decide the order of the filter. That which order will you take? First order, second order, third order, fourth order. Somebody says, what would be the impact? What would be the impact of the order? The order means basically higher the order of the filter, difficult it is to design it, difficult it is to realize it. But then also why order is required? The more appropriate see for basically image smoothing than the ideal low pass filter, since it does not introduce ringing. So smoothing, yes, definitely. Smoothing can be controlled by the order, see, because higher the order is there. See, I draw you. Here, both image processing and signal processing meet. Yes, to minimize the error. For example, see this filter, this is some filter. And what is this? This is basically the R now. And this is basically the R. So this is on the x-axis R, and here it is magnitude. That what is the magnitude of the frequency that is present? This is HU of P. Remember, so what is actually, see, this is very higher order. So what is basically realizable? Realizable is this one. This one. This one. So see, when you go through it, so many parameters will come in picture. This sharp clink, etc., is not easy to achieve. They are really always difficult. That has been said here. So that's why it has been shown. See, as the order becomes higher, see, why do we go for the higher order filter? If we want to achieve these type of kinks, sharp transition. Otherwise, in lower order, it is a smooth change. And remember, designing higher order filter, again, it requires higher cost and it is time taking. So what it has been saying that this is more appropriate for image smoothing than the ideal low pass filter, since it does not introduce or. So what do you mean by the smoothing? Smoothing, see, it is the same concept. Smoothing means we are leveling out. For example, some noises, they are low level noises there. We are able to remove that noise. That's how we are able to do it. So now we take up some examples, some original image is given, and this image, what do you see here? That R naught, we have taken basically the different value of R naught so that it can be demonstrated well. Now, when you are, as we have already seen it, When we are taking basically R not 18, so this is basically, see, this is original image, this is more closer to the this. Here it has become actually blur, and here it has become very much blur. Now coming to the high pass filtering. So what do we do in basically the high pass filtering? High pass filter is again, see if we draw it here. So here it is another thing. Here it is R naught. Here it is 1. So what is saying that after R naught it becomes 1 and before R naught it is 0. The relationship has been changed here, right? So only the purpose here is that some information many times it is in, so what it has been, it is exactly said here that it is used for sharpening the image. It is used to sharpen the image by attenuating low frequency component, means we decrease it and preserve the high frequency component. The mechanism is given, high pass filtering in the frequency domain is given by this thing where, so it can be also related to this one. So now we can see the examples of what will happen in the high pass filtering. And high pass filtering, it has been shown here that R. Now see, remember R naught value, if it will be more, then it will be the other way, right? So when it will be less, then it will be more information. So what we are saying here R not equal to 18, so you are able to see the sketches. But when it has become very much large here, you are able to see, even it is bit difficult to observe than this one. And even at R not equal to 36, it has become almost difficult. See, if I do not see the original image, I may not able to find out the actual image. This is the way of the different value of the parameters in the hyperfiltering. This is another topic, basically the image compression. So in image compression, see what do we do? So there we basically conclude the thing in earlier. What the image enhancement, that part is completed. Now another problem is there, that is image compression. Any question? Better we take a break here. So I think so that we can come again, right? But because it's a new topic, we will cover it. Assignment marks, so then yes, definitely, yeah, that we will give it together. We see more or less here, see all it is based on the basically giving the certificate. No more actually, we are not preparing any rank, etc. It is basically to motivate you for the learning, to grasp the thing, instead of make it like again competitive thing, which we most of the time follow in our life. That is being bit disgraced here. Mainly upon the self-learning, if you are able to see, after the end, you are able to have a confidence. So we will meet after a short break of 10 minutes. So, hello, welcome back. You see, one question was there. See, what is the correct solution? Correct solution we have just discussed this. Sojan, I think we were a bit late. Already discussed it. Told the correct one. Are you here, Sojan? So now, yes, we have already discussed it. It's a simple problem that is based upon same thing. Even see if you want it, we will see it in the afternoon. We can see that what is its part, right? No issue. So now coming to the part, see image compression. Remember, see image enhancement. Now under the umbrella of the image processing, one part is image enhancement. Where is the basically image enhancement used? See, for example, when I am basically taking the photograph here. For example, I am recording the video in the CCTV. Then to enhance the image quality. For example, I have to take some decision in some any criminal case, etc., or in any critical issue, then image enhancement is required. See, thereafter, then cases there, for example, remote sensing. Many images are basically which are taken by the spacecraft. Those images, see their see if you are aware, see what do they do? Send in the spacecraft, they send the camera actually, which is attached there. So which is orbit and they take it the different photograph. So you interpret those photographs. Again, see you don't have you don't have the control that you can change the position of camera or you can retake it. So again, there the image enhancement becomes very popular. So these are the key areas where it has been become very necessary. Image now coming to the image compression. Image compression has becomes very critical when you basically communicate. Whenever you communicate, image compression is required. For example, even when uh, I am communicating with you people, the image compression is very much required because see the data bandwidth is limited. As soon as the user, day by day, as the number of users are going up and up, the demand of the image compression has also become very large. So that's why we now the very much focus is on the image compression. So it's basically a separate branch. In image enhancement, it is about basically the better look, better recalling the information from the image. But in image compression, it's about the size. Somebody very well questioned it in the beginning, says that what is basically the parameter which is used for the image enhancement? It is basically more or less it is said by the appearance and see which type of details I am able to recall from that image. See, for example, minute details of the nuts, etc., which were not available in the original image. So parameter wise, it's very difficult to tell. But in compression sheets, we can tell the parameter. It is basically the how much bits, in number of bits, reduction in the bits. That is basically the unit. Here it's very easy to define the unit in image compression, but in image enhancement, it is not that easy. It is depend upon the task. But all they come under the part of the image processing. So what is image compression? Image even see when we are doing basically this MPEG file, this MP4, JP4, JPEG, etc. Are you aware? See what is this JPEG, MPEG? जो आप ये अपने but you save your basically image file. Are you aware what is this JPG, MPG? What is this? Can you tell? JPG, MPG. What is this JPG and MPG? Photoshop, JPG format, joint photography. Yes, actually, yes, it's a joint photograph, but actually it's a compression standard. If you will go into its detail, these are basically the compression standard, that how much compression is followed here. Because see, these files, same files are used to transmit it. Definitely, they compress to take less storage, but these are the formats actually. JPG format, MPG format, that much compression we are doing it. When I'm saving my image on the computer in the JPG form, so it is that much compression. It, that much compression will be done when I will say in JPG format, MPG format, etc. So these are basically the compression formats. That's why these names are there. Yes, see, compress with quality, definitely. See, size is there for quality, and see quality in such a way that you are not able to notice the change. Because if there is a degradation in the change, then the purpose is not served. Change should be up to a level only that it shouldn't be a problem to a user. Now, formally reading it, what is the image compression is used to make image file sizes smaller, right? Used to make image file sizes smaller so that they can take up less space on computer and can be shared faster over the internet. The goal is to reduce the file size without changing. The very important thing here. Reduce the file size without changing how the image looks. Computer images are made up of tiny blocks called pixels, and each pixel stores an information intensity value. When an image is very large, it contains millions of these numbers, which means the file size becomes large. And remember, even the image compression also becomes very important because these days, see, one trend is happening that as soon as you take up the mobile, see, these mobile, etc., they are providing the very higher order, high resolution camera. It has become the feature of individual device. Earlier, see, it was 1 megapixel, now 10 megapixel, it is 100 megapixel. So remember, as soon as the size is so, the what is happening, the size of the image is also becoming very large. And size of image is becoming very large, then what do you do? When you are basically taking up a photograph, you will share over an WhatsApp. I will send to my friend, I will send to my family member. So what happens? See, then it becomes even a more issue. So your mobile is actually creating a problem, these new mobile. So if really for the ideal condition of the image compression, these new mobiles shouldn't be allowed, or they should not come with this feature where you are basically increasing the resolution of camera. So data compression, so image compression is a specific task. We go to the higher level. What is data compression? Data compression is basically is the process of encoding data. As we told it that JPG, MPG, these are basically the coding standard, so that it takes less storage space or less transmission time than it would if it were not compressed. This is the thing. It is basically encoding. These are the encoding data. Data compression, it is basically mathematical process of transforming data to a smaller representation from the origin. So original bits, for how can I be understand it? Original data, if it is n1 bits, compressed data is n2 bits. So if n1 is equal to n2, it means there is no compression. If n2, the resultant thing is very, very less than n1, then there is a significant compression. But if n1 is very, very less than n2, then it is a data explosion. Data explosion, which we are really talking when uh, when we are seeing this case. So now coming to the part image compression is fundamental. So what are the other things? So let B and B dash. See, whenever we want to understand the concept against the mathematical terms gives us the precise meaning of these things. Let B and B dash denote the number of the bits in two representations of the same information. The relative data redundancy R of the compression with B bits is basically R equal to 1 minus 1 upon CR, where CR commonly called the compression ratio is defined as this. So what it is saying here. So if there is B equal to B dash, means after there is no change, then R equal to 0. R equal to 0 and CR equal to 1, it means no data redundancy. It can't be changed. What basically B dash in that it is the different type of representation systems are there. So this is basically the two type of different representation, two type of different encoding. See, one is basically one original one, another is another encoding scheme. When we are saying if CR equal to 10 or 10 is to 1, it means larger representation has 10 bits of data for every bit of data in the smaller representation. Right? What it is saying that if B equal, this is the case, 10 is to 1, what is basically CR is basically this, E upon B dash. So what we are saying, so what we are saying that larger representation has 10 bits of data for every 1 bit of data in the smaller representation. Corresponding relative data redundancy large representation is 0.9 indicating 90% of data is redundant. So actually from the CR actually you get to know that how much reduction is possible. So if equal to 10 is there, if 10 is to 1, it means definitely lot of scope is there. If CR is basically very less, then definitely scope is very less. If CR is more than scope is very large. Come to the type of redundancy. So what type of redundancy? There are basically the data redundancy. It can be the redundancy means where we can basically can we reduce the information. Can we reduce the information without using the basic structure of image? So whenever we so data redundancy coming to it, two type of redundancy is involved. Basically, one is coding redundancy, another is spatial and temporal redundancy, and thereafter it is the irrelevant information. So in each piece of, so what is basically the coding redundancy? Coding redundancy, the each piece of information or event is assigned a sequence of code symbol. That is basically called a code word. The number of symbols in each. So what do we do? You notice it here. Each piece of information or event is assigned a sequence of code symbols. See, as you have, if you recall, in the last part, see what did we notice, that it is a process of encoding. Encoding means basically with some rule you convert into another form, another number. For example, we convert our normal decimal number into a binary number. That is basically again the encoding. So it is assigned a sequence of code symbols called a code word. The number of symbols in each code word is length, right? So this is the thing. Pixels of most. So what is basically what is shown here? See, for example, some code, maybe some code write the thing require the 50 words to write 100 word, and some code require only the 30 word. So here it's a redundancy of the 20. That's why it is basically at the encoding level. What do you mean by the spatial and temporal redundancy? Pixels of more, see, whenever spatial is coming, so it is basically the pixel. So pixel of most 2D intensity arrays are correlated spatially. Especially now, see, very important thing that earlier, see, we have taken the neighborhood information along with pixel to note down the impact of mass. But now what they are saying that the pixel value is itself correlated. It means the pixel has some correlation in their neighborhood, right? So that is very another interpretation. Even see, we people, our research team, what we are basically using the concept graph signal processing that also captures that thing. That your pixel itself, they have also some correlation among each other, some interrelationship among each other. But how can you say that there is some interrelationship? We can say, see, there is some interrelationship. For example, see, if you are taking basically a picture of some face, when you are taking picture of face, so some definitely there will be some pattern. For example, my eyes is here, my nose is here. So definitely see some region it will be, yeah, some common pattern. If here it's eye, so here things are almost fixed. Means even exactly I don't need the information. If you simply give me the location of the eyes and the nose, I can we can nearly depict the face of the person. So that's why we are saying that pixels are also correlated spatial. This is very important observation. Information is unnecessarily replicated in the representation of the correlated pixel. So that's we are saying the same thing that many times it is information is repeated again and again. Irrelevant information. What do you mean irrelevant? It is most 2D intensity arrays contain information that is ignored by human visual system, or they are extra to the intended use of the image. It is redundant. So what we are saying, see, it is not required for the purpose, for the actual purpose. See, for example, here see this, for example, here this image is there. So in the background, some color is there. But see, this color is not required. If somebody is asking me to calculate the number of birds, to calculate the number of words in an image, then this background information, etc., doesn't matter. Only what really matters, it is basically that word only. What we are saying that most 2D intensity arrays contain information that is ignored by the human visual system or extra to the intended use of the image. That is any question. So it's a new concept. Okay. So we have read basically the three type of redundancy: data encoding, spatial temporal, and irrelevant information. Please be clear that spatial and temporal, that the temporal way basically it is the same thing. Because there in the time domain actually becomes that is almost included in the space only. That's why, except the some special cases, this spatial and temporal will remain same. Now, see, coming to the part that how we are able to do this coding, how will we able to do the mathematics? So, in mathematics, is coding redundancy. How we can do it? So, for example, so it is assume here that the discrete random variable for R subscript k in the interval 0 to 1 that represent the gray level. So, each R of k occurs with probability P of k, right? What is this R of k? It is basically the discrete random is given in the interval. So this is given 87, 128, 186, 255. So this is the one. For other value, it is 0. So is the number of bits. Thereafter, what is he calculating? He is calculating the probability distribution function. How we can calculate it? It is the same way. What way? That we have done earlier in our histogram equalization. So 87 plus 128 plus 186 plus 255. So when you will calculate, so when you will add, do the its addition, and when you will divide it, you will get 0.25. Here you will get 0.47, and here you get basically 0.25, and here you will get the 0.03. And so what will be basically the code of this one? Code 1, and so the number of bits basically which used to represent each value of R of k by L R of k, then L average is basically L R of k multiplied by P R of k. So what is this L R of k? It is basically the how many number of bits which are required to represent it. So that has been here. The average code bits assigned to the gray level values, the length of the code should be inverse proportional to its probability. So what is being shown here? So basically code 0 2, it has been shown here 0 1 in the MSB, it is a 1, it is the 186. So here it is given 0, and then code 2, it is given 001. In L2, when you will convert this value, it will become 2, it will become 1, it will become 3, 3, and this is 0. So what we are saying here that what will be the L average? L average will be the same formula, L into this one, 2 into 0.25 plus 1 into 0.47 plus 3 into 0.25 plus 3 into zero point 0.3. So when you do it 3 into, so what you will get L average, basically it is saying that it will require basically 1.81 bits, right? So average code bits assigned to the grade level value. Now what we are saying, there is a length. So what will be the CR in this case? CR is again say 256. So this is basically 1.81. So its formula, it is B upon B dash, and when B is equal to 256 into 256 into 8, so B dash is 256 into 256 into 1.81. That you will get 4.42. So thereafter, what we are calculating the R equal to 1 minus 1 upon CR. What is CR? CR is again B upon B dash. So when you will calculate it, so R is basically 77%. It means that much scope of redundancy is there. Now coming to the part is spatial temporal redundancy. So what we are doing in the spatial temporal redundancy? It is basically the spatiality, as we already noticed that there is an in-between relationship between the pixels. So what we are saying here that it is internal correlation between the pixels. Internal correlation between the pixel. Uh, so what is it is result from the respective autocorrelation, structural relationship, geometric relationship, right? So value of a pixel can be reasonably predicted from the values of its neighbors. To reduce the interpixel redundancies in an image, the 2D image is transformed into more efficient format. What do we do? We basically transformed into a frequency domain, etc. What you would do after considering into frequency domains is then you can basically remove the whatever except the required frequencies you can able to use the filter and then you can remove it. Irrelevant redundancies. Irrelevant information. Here, see what we are saying that the many times many colorful information, many objects are there. But see, when our uh, purpose is there, then it doesn't serve any purpose. The brightness of a region depend on other factors that are other than the light reflection. The perceived intensity of the eye is limited and non-linear. Certain information is very less relative importance, so which is not required at that time in normal user process. Even in general, see observer searches for distinguishing features such as edges and textural regions. So what are basically the steps in image comparison? Because see, whenever we are doing this, there should be some algorithm. So we will go through the algorithm. So what is so overall? See, for example, pixel by pixel. Now we take the initial problem, black and white image. black and white image with a resolution of this much. So with a resolution of this much, so total number of bits, how many? So these many pixels are there, and so total pixel will be 1000 into 1000 multiplied by 8. So it is basically 8 lakh thousand bits per image. So if you consider a video with the 30 frames per second of that image, then the total bits for a video of 3 seconds is 3 into 30. So this is the case. So that many number of bits are required. So what do we do? So to store a 3 second video, we need so many bits. You can imagine, see, it is almost 7 crore, 20 lakh bit, right? So actually it is 72 uh, crore bit. Can you imagine? Such a high number. So what do we do when such a in form of bits? So first step, when we transform the image data into a new form that is easier to compress, it rearranges the image information so that the important parts are more noticeable and the unnecessary parts can be reduced. This is a key thing, that whatever we want to focus upon, that can be. So there actually in the sub part of the image, we apply the image enhancement. And thereafter, when it is clear that this part is not required, this part is not required, then we can do the image comparison. So here we use basically a transform, like the discrete cosine transform that maps from one domain to the another domain. Assume that T is a transform with ft from x to f is a function, and txt is called basically the transform of the function. This is the way. So these are becoming the tools: discrete cosine transform, etc. What is basically the stage of the encoding? In the stage of the encoding, basically three parts are there. That is, mapping is there, then quantization, then symbol encoder, then source decoder is there, and then inverse mapper is there. So what we are doing here, basically remove interpixel redundancy. Interpixel redundancy is pixels that are correlated or very similar. Mapper converts raw image a new representation where redundancy is reduced. So for example, we may use the transform coding, DCT, and the DWT. It's the quantizer. And the quantizers, if you see the human, I can't notice very tiny differences. Quantization and approximate values, so fewer bits are required. And thereafter, so there when we notice it here, then human eye can't notice very tiny differences. Quantization, approximate value, so fewer bits are required. So again, as we considered earlier, that it is rounding, it is uniform quantization, JPEG quantization table is used. And finally, we use, so first we do the mapping. After mapping, it is quantization. So what happened in quantization? In quantization, see, even see yesterday also we had been doing the quantization, that rounding of the thing. So what is the purpose of coding redundancy removal? Coding basically it is converts quantizer output into fixed length or variable length code. So So here it is basically Huffman coding, and here it is arithmetic coding, and here it is run length coding. So that's how basically we used it in this part. In the source decoder and basically inverse. Thereafter, see the three part was the encoding part, remember, for compression. But to again retrieve back the information, this part is also required, that is the source decoder and the inverse map. This is source decoder and inverse mapper that is equally required because we finally want to originally see the image. Compression is only required till the part when you transmit it over a channel. Just we take a 5 minute break so that we can have some kind of session change. Actually, we have a 2 hour. This is there, so that recording etc. can be changed. We just take a technical 5-7 minute break.